Hi, I'm Stephen Herwig. In this presentation, I will be talking about my work in building keyless content delivery networks. This is joint work with my advisor, Levin, and our collaborator, Christina Garman. Suppose we log into our bank's website to pay some bills. Although we envision our browser connecting directly to the bank's web server, the truth is that the bank and many other websites use a third-party service called a content delivery network, or CDN, to host their website. At their core, CDNs are a massive global network of physical edge servers that act as caches for the customer server. Although the traditional value add of a CDN is improving a site's speed, CDNs also provide security by mitigating DDoS attacks and running web application firewalls that block targeted attacks. In order for the edge server to serve content over HTTPS, they must have access to the website's private key. In practice, the customer shares their private key with the CDN, and this key is placed on each of the CDN's edge servers. In fact, a study from 2016 found that 43% of the Alexa top 10,000 share their keys. Key sharing, of course, brings many concerns, as the CDN is now a man in the middle, and trust for the web as a whole becomes consolidated to just a handful of providers. I should also note that CDNs generally don't even want to have their customers' private keys, as this raises liability issues. To address aspects of this problem, Cloudflare developed the keyless SSL protocol, which allows CDN customers to maintain sole ownership of their private keys. Keyless SSL takes advantage of the fact that TLS only uses the website's private key in a single step of the TLS handshake. And so with keyless SSL, the CDN's edge server proxies the handshake to a customer-controlled key server, and the rest of the web request is handled by the edge server. However, even with keyless SSL, the CDN operator still learns all the session keys. Moreover, in practice, customers ask the CDN operator to run the key server on their behalf. Thus, the actual benefit is not for the customer to retain custody of the key, but rather to mitigate against Heartbleed-style vulnerabilities. CDNs are just one specific example of the broader problem of organizations outsourcing their applications or infrastructure to a third party, despite exposing private data about themselves in the process. Beyond CDNs, my broader question is whether we can maintain privacy using legacy applications on third-party resources. In this setup, we assume that the content owner and the third party agree to run on the third-party server some software that the content owner trusts. We assume a threat model where the third party can arbitrarily interfere with the software, and our goal is to reduce the third party's adversarial power to that of a network-level TLS attacker. As a central goal and distinguishing feature of this work, I seek solutions that are compatible with off-the-shelf software. In particular, I don't want to have to rewrite software from scratch to achieve these security properties. Now we have the building blocks to start solving this problem. The challenge is to compose these building blocks into a coherent, meaningful system. Let's focus on building up this system and then come back to building a CDN, specifically Phoenix, with this system in mind later in the talk. As our core building block for secure remote computation, we use Intel SGX. SGX is an extension to the x86 instruction set that allows a process to define a private region of memory called an enclave. SGX guarantees via hardware security checks that software outside of the enclave, and even a physical attacker, cannot observe or alter the enclave's state. In practice, various side-channel attacks have undermined this guarantee, and in this particular iteration of our work, we treat mitigation as an orthogonal concern. The first challenge is to design and implement an execution environment that handles the restrictions of enclave mode to run such legacy binaries, the most obvious restriction being that enclave code cannot make system calls. There have been a few projects that seek to take legacy binaries and run them in an enclave. The general idea is to move libc and part of the operating system kernel, now refactored as a library, into the enclave. libc is patched to invoke the libOS for system calls, and the libOS proxies to the untrusted host for any system call that it cannot service internally. The specific libOS implementation I built off of is Graphene SGX. With this LibOS design, Graphene provides a foothold to add and emulate additional features. For instance, Graphene's main added feature is allowing an enclave process to fork a child process, which itself runs within an enclave. However, to run software, such as a multi-process web server on the CDN's edge, we also need Graphene to securely emulate additional resources that the various application processes share. With Conclaves, my contribution is extending the enclave security guarantees beyond private memory to these other shared system resources. For instance, the hard disk and shared memory, and incorporating the respective driver components within either Graphene or the plugin framework of some core user library. My insight is to think of the application and its execution environment as a distributed system of processes, each running within an enclave. This leads to a microkernel-inspired architecture where kernel services, such as the file system, shared memory, or an application key store, are implemented as dedicated servers running within an enclave, and where an application's underlying instance of Graphene proxies a system call to the appropriate server. As the design contains multiple enclaves, there is the need to bootstrap trust in the resultant distributed system, and ultimately provision it with private data. This part of the work is still a work in progress, but it follows from prior work, and the connections between the enclaves are mutually authenticated and attested TLS connections. As an initial kernel server, we implement a key server as a type of SGX rendition of a hardware security module with a companion OpenSSL engine. We also develop several implementations of shared memory, all implemented as file systems within Graphene that expose a memory file abstraction. In one version, the application opens and nmaps a file on such a file system, and then uses the fcontrol system call to lock the file. The Graphene libOS services the call by making an RPC to the memory server. The memory server manages the shared memory segment as an encrypted host file, as well as managing the lock owner and keying material. On acquiring the lock and keying material from the server, the libOS reads the encrypted memory segment into the enclave, decrypts it, and updates its memory pages. Finally, for an encrypted and integrity-protected file system, we convert a user space implementation of a standard Linux file system into a server. We then run that resultant file system server on top of Graphene. We emulate the hard disk by formatting a large untrusted host file as the backing store. On a file system-related system call, the libOS again proxies the call to the file server. The file server implements a block layer that decrypts the virtual blocks on read, while also maintaining a Merkle tree over the entire backing store. I use the term conclave to refer to such a collection of cooperating enclaves. To the application, use of these kernel servers is either transparent modulo and application configuration option, or requires a small patch, as with the memory server. Coming back to the CDN use case, I use the term Phoenix to refer to NGINX, configured as a reverse caching proxy running within an enclave, as a sort of conclave analog to an edge server software stack. In our paper, we discuss other details, such as how customers could securely delegate provisioning of the conclave to the operator. We also discuss deployments where conclaves can contain multiple parties. Now, as a macro benchmark for evaluating Phoenix's performance, I use a web server stressing tool to measure the web server's throughput, varying the size of the file and number of NGINX worker processes. As a baseline, I first evaluate NGINX running outside of a conclave, what I term in the legend as Linux. As you can see, the throughput varies between 800 and 3000 requests per second, depending on the configuration and workload. I next compared two configurations of Phoenix Crypt and VeraCrypt. The kernel servers for Crypt only offer confidentiality of their respective resources, whereas those of VeraCrypt also guarantee integrity. With these workloads, Phoenix Crypt's overhead is roughly 2 to 3 times that of Linux, whereas VeraCrypt is between 3 and 14 times. Needless to say, this isn't great, but nevertheless it's a very promising start for what amounts to an unoptimized system. We next evaluate conclave approaches to multitenancy, which is hosting multiple customers on the same edge server. In this evaluation, we scale the number of tenants from 1 up to 6, conduct a stress test, and then compute the mean time to request a 1 kilobyte file across all tenants. At these tenants' numbers, the non-enclaved Linux baseline exhibits a latency that grows sublinearly with the number of tenants. In our first conclave approach, called Share Nothing, each customer runs their own conclave, including their own dedicated enclaved instance of NGINX. We see that request time increases roughly quadratically with the number of tenants. If we instead use an approach where tenants share an enclave NGINX, but use their own kernel servers, then request time increases only linearly. Now it's interesting to also plot the number of SGX paging events during these tests, because we see that somewhere between 32 and 48 enclaves, there's a dramatic increase in pressure on the limited EPC memory. The take-home message is that supporting massive multi-tenancy indicates a deployment where customers share enclaves. We include many other results in our paper. Please check it out. In conclusion, users continue to outsource their applications and infrastructure to third parties, and in doing so forfeit privacy. In this paper, we present the design and implementation of conclaves, an extension to the Graphene SGX LibOS that runs legacy applications safely on third parties by, among other things, extending Graphene's protection to the file system and shared memory. I've enjoyed sharing this work with you, and I encourage you to explore conclaves for use cases that you may encounter in your own research.